Now, if you go up from Sirius and over to the left, you eventually come to a star which is sort of in an area of sky more or less on its own. And this star is known as Procyon, and it's the brightest star in the constellation of Canis Minor, the little dog. Now, if you join a line from Sirius to Procyon, and then from Procyon to Betelgeuse, and then down to Sirius again, you form an unofficial pattern in the night sky known as the winter triangle. Okay, we return to Orion again. We can use him as a signpost once more. If you go from the star in the bottom right-hand corner, that's Rigel, draw a line through the star in the upper left-hand corner, that's Betelgeuse, and keep going until you come to a pair of stars. Now, this sounds a bit of a strange thing to say because any two stars are going to make a pair, but these two really do look as if they belong together. And so they should, because these are the two brightest stars of Gemini, the heavenly twins. The upper star is known as Castor and the lower star is known as Pollux. Now, there is going to be a very special event happening in the middle of December. We have a meteor shower known as the Geminids. And the Geminids is so called because the meteors which occur from it appear to emanate from a point in the sky known as the radiant, which is located very close to the star Castor. Now, if you go out on the night of the 13th, 14th of December, you stand a very good chance of seeing a Geminid meteor streaking across the night sky. We have a number of benefits this year with the Geminids. For one, the moon is going to be completely out of the way, so the sky should be very, very good and dark. We also have the fact that the radiant, the position where these meteors appear to come from, should pass more or less overhead at about 2 o'clock in the morning, and this is ideal for meteor shower watching. So give yourself plenty of time on the night, use watches of at least 30 minutes, say, go out in the middle of the month, look up skyward, and see if you can see one of these beautiful Geminid meteors streaking across the heavens.
Back to the garden, into my study with Chris and with our guest, Professor Bob Nichol. Welcome, Bob. I know you're involved very deeply with a project called Sloan, so can you please begin by giving us a brief rundown on Sloan?
The Sloan Digital Sky Survey started taking data in the year 2000. At the time it started, it was the world's biggest camera, so it's a very, very large digital camera. It has a 142 megapixel camera in the optical, and in addition it has 2 spectrographs. So it's able to take very large images in one shot of the sky, much greater than the diameter of a moon. That allows it to wallpaper the sky, because it can take many images and put them together, and thus do a whole digital image of the night sky. So you can have that in your computer and be able to dial up any position on the sky and get an image for it.
And similarly, you can cover the whole sky quickly, but you can also take lots of spectra at once as well.
Exactly. In the original Sloan, we had both a digital imaging camera and a spectrograph. In Sloan 3, we're actually getting rid of the digital camera because we don't actually need it anymore, and we're going to concentrate on the spectroscopy, as you point out. So we'll do lots of spectra across the night sky rather than lots of images.
So why throw the camera away? Why take spectra instead of images? Images are better to look at.
Well, you're right, Chris. You know, to our eye, an image of a galaxy, a star, is much more appealing. But the imaging camera in Sloan is now no longer unique. There are bigger imaging cameras coming along, and we've taken a digital image of the night sky, and we've made it available to the public, as you know, through projects like Galaxy Zoo. What's still unique about the Sloan hardware is its ability to do massive amounts of spectroscopy across this large field of view.
So you take the light from an object and split it up into its wavelengths.
Exactly. So when you're looking at those wonderful images and you make them up with red, green and blue, that's sort of a spectrum of 3 colours. Imagine now having a spectrum of 2,000 colours, and that's really what we have, is you split the light up into all its little individual colours, and you're able to see quite subtle features. You're able to see atomic features, so you can tell what's in the object you're looking at. You can tell what atoms are in the object, and that's why spectroscopy is so important. It's like chemistry. You're doing chemistry on these objects.
What will Sloan tell us about the stars in our galaxy?
So, Patrick, for Sloan 3, what we're planning to do are 2 new surveys of stars in our galaxies. One is Segway, which is a continuation of the optical spectra of stars in the outer regions of our galaxy. But the really exciting one is something called apogee, and this is a new survey using a new infrared spectrograph. And what apogee will do for the first time is be able to look at stars in the disk of our galaxy through all that muck and dust that is in the disk of our galaxy. And as you know, that extinguishes optical light, so you can't see very far in the optical. But in the infrared, you can see much further through the disk of our star. And in fact, we hope with apogee that we'll be able to look at stars in the bulge of our galaxy. So we'll be able to measure the dynamics and also the spectral characteristics of stars in our bulge.
So the bulge of the galaxy is the blob at the centre, right?
Exactly.
If you imagine, I always think of your analogy of two fried eggs.
Two back to back, yes.
So if that's true, the bulge must be the yolk, right? The yellow bit.
Yeah, and in fact, that analogy is perfect because the yolk is yellow, and yellow stars tend to be old stars, right? And the fried disk bit, the white bit, is the disk, which we think is made up of young stars, which typically are whiter and bluer. So actually, the fried egg analogy is perfect.
And all we've looked at so far with the optical in our galaxy is the white bit.
Sure, or straight out of the white bit. So we've looked out of the plane of that of the egg. As you know, what's kind of interesting is that big blob or that yolk of old stars, that bulge of stars in the center. And if again our theories of galaxies are correct, that bulge formed first. That was the first thing put into place in our galaxy.
Well,
How far away is it?
So it's about 8 kiloparsecs.
So you need
don't
to
ask.
convert to light years.
Yeah, I knew you.
Multiply by 3. So what's that? That's 24,000 light years, something like that.
Thank you, Chris. That's where we have them on the program. But it's extremely difficult to look at the bulge because you have to look straight along the galaxy, straight through this disk that's made up of dust and muck and rubbish that is in our galaxy. And you can do that much easier in the infrared. So Sloan will do a survey of infrared stars along the disk of our galaxy.
And we'll see whether these stars really did form in one blob in the centre of what's now the Milky Way, or whether presumably they could have come from mergers or from somewhere else.
Exactly. So what will be wonderful is, are they a homogeneous population? So if you look at their chemical abundances, like how much calcium's there, how much oxygen is there, are they homogeneous in terms of were they all formed at the same time, or is there a mixture? And in fact, what's very interesting is potentially we may find very metal-poor stars. And those are the types of stars that could have been formed from the very first stars in the universe, something called population 3 stars. And again, you need to look at a lot of stars to find these one rare objects.
How old are they?
So the population 3 stars could have literally formed just after the cosmic microwave background, which is about 300,000 years after the Big Bang.
So more than 13 billion years ago.
More than 13 billion years ago. So these would be the oldest stars made up of the pristine material that was around just after the Big Bang.
We should talk about Sloan's new role as a planet hunter as well, because that's an obvious advantage of this wide field of view that you've been describing. We can go searching for planets as well.
So this is the MARVELS project. MARVELS is again another new spectrograph that is using the Sloan telescope. It can observe 120, or will do soon, 120 stars simultaneously. And the beauty of MARVELS is it makes incredibly accurate spectral measurements of those stars. And what it looks for are the wobbles. It just looks for the radial velocity wobbles of those stars.
So this is the star being pulled by planets that are around
Exactly,
it.
exactly. So what you do is you see a lovely sine curve to the spectral measurements of the stars, and you can infer from that that there must be an object going around it, as you say, pulling on the star, and you won't see the star, but you can see it's, you can sort of see it's there from its effect on the velocity of the star. So we expect Sloan to find about 200 Jupiter-like objects, and hopefully those solar systems contain Earth-like objects, and so there'll be a wonderful opportunity to try and find other planets, other Earth-like planets out there.
If you don't, the yoke will be on you. I'm sorry. But what about the bar right through the galaxy?
Just in case people are not aware, that your fried egg analogy for the galaxy potentially is inaccurate in that you might need to have a fish finger across the top, in that we think there's this bar structure in going through the centre of our galaxy.